Hello, hello, everybody. All right, so this lecture is corresponds to the day in the schedule that says Inferential Statistics, semicolon, continuous variables. So in this video, we're going to be talking about t-tests and correlation, right, which are the analyses that we do when our outcome variable of interest is continuous, all right? That is, it's measured on an interval or ratio response scale. If you have not taken the time to look at them yet, on the YouTube channel, if you click on the playlist button, I have added some videos, some from Khan Academy, some just, made by teachers at other universities. I really, really love, let me see if I can pull it up so you guys can see it. Probably not. Here it is. All right, so I really love this video right here, made by a guy named Greg Martin. He's an editor for a journal. He's not a marketing guy, but I think that his video does a really good job of explaining a lot of the things that we talk about in the intro to inferential statistics video. It's like, why do we have to do this in the first place? What does the p-value mean? And then he talks about the he talks about 5 of the 6 tests that we learn about. And he does it in a way that I think is really clear and easy to understand. He says data in an unusual way, but besides that, I think that the video is really good. So I would definitely recommend going to the YouTube channel and watching this video. You can see it's only 13 minutes long, and hopefully it'll give you a big picture look at what it is that we're doing with the statistics. And hopefully it will be helpful in helping you decide which test is the appropriate kind of test when you're doing your data analysis plan assignment. All right, so let me get rid of this stuff that you guys don't care about. All right, let's talk about t-tests and correlation today. All right, so if you'll recall when we were talking about chi-square tests, I said that we needed chi-square tests because we were looking at nominal data, and because we had that nominal data, we could not, apparently there's a tornado watch, we could not report means. All right, so t-tests deal with means. All right, so if you have calculated a mean response to something, and then you have a question about that mean at the population level, you're going to need a t-test to answer it. All right, and we're going to learn about 3 different kinds of t-tests. You can see the names right here. If you have one question from your survey, everyone in your sample answered 1 question on the survey. You calculate the mean response to that 1 question, and now you want to know, is that mean response equal to some external reference point number that I'm interested in? Kind of like when we did the chi-square goodness of fit, we're comparing our sample's answers against some external reference point. You're going to use a one-way t-test. If you want to divide your sample up into 2 groups, all right, so for example, you put the men in one group and the women in another group, and then you look to see those men and women, did they answer some other question, all right? For example, going back to the intro to inferential testing video, their purchase intentions, if you wanna know, is the mean response for the men, purchase intention mean, different than the purchase intention mean for the women, we need an independent samples t-test to do that. And the paired samples t-test, which is a t-test that is not discussed in that YouTube video that I was just saying that I really like, but we'll talk about it today and I'll give you some examples. Everyone in your survey answers 2 survey questions. Let me see if I can get this table pulled up. This one falls right here in this table down here. We are not going to divide our sample up into any groups, all right? Everyone in the survey answers 2 continuous measures. That's what this continuous 2 means. Everyone in your survey has answered 2 questions, and now we want to know is their answer to question 1 equal to their answer to question 2. All right, and so for example, you might ask, how much do you like marketing research? How much do you like consumer behavior? You can take everyone's answers to those 2 questions and ask, is the amount that people like marketing research different from the amount that they like consumer behavior? All right, so we're not dividing people up into any categories to see if that category membership predicts how they answer these questions. We're just looking to see, is their mean response to question 1 different from their mean response to question 2? And we do that with a paired samples t-test. All right, so in this video, I'm going to show you examples of all 3 of these with some, practical sort of data that I got from that student survey. And then we're going to turn and talk about correlation. All right, so let's jump in. One-way t-test. Remember what a one-way t-test does. Let me do some horrible writing with this pen. We are going to observe in our data set, all right, so we drew a sample from the student body. We have this sample and we're going to observe a mean response on some measure. And then we're going to ask, is that mean response equal to some number? All right, and that some number that we specify can be anything. It's just going to be specified by the question that you are asking. All right, so in this case, if I have this question, do college students eat more than half of their lunches away from home? All right, I asked on the survey, how many days per week do you eat lunch away from home? And so what I'm asking is, it's possible that students are not eating more than half of their lunches away from home. All right, and so my null hypothesis is that the number of lunches that they eat away from home equals half of the days of the week, all right, 3.5. Or it's possible they are eating more than half of their lunches away from home. And so my alternative is that the number of lunches eaten away from home is not 3.5. All right, so it's either more or less than that. Looking at the data from the survey that I gave my students, the range that we saw was 0 to 7 days. Some people said they always eat at home. Some people said they never eat at home. And the mean was 3.94. All right, so the data in our sample has provided us now with some evidence that maybe students eat more than half of lunches away from home, right? Because 3.94 is mathematically greater than 3.5. The question is it statistically significantly different? All right, is this difference between 3.94 and 3.5 large enough that it's unlikely to have occurred due to chance and sampling error? All right, and so to answer this question, we have to actually do the one-way t-test. All right, in SPSS, all these things that I have open down here. In SPSS, to get to a one-way t-test, we're gonna go to Analyze, Compare Means. All right, all of our t-tests are here in this Compare Means menu. So we're gonna go to Compare Means and One Sample t-test. In this menu, it looks kind of similar to the chi-square goodness of fit menu. All right, so we have all of our variables over here. We're gonna move the variable we're interested in to the test variable box. In this case, we are interested in, what did I say, lunches out? All right, so we're gonna move lunches out over to the test variable box. And instead of specifying an expected distribution, here we have to specify a test value, all right, because we don't have a distribution. This is not a nominal response where people, different proportions of people circled each possible option. Here we just have one number that we want to compare our mean against, all right? And so in this case, that value is 3.5. We're gonna come back to this line right here in just a second after we do this test. All right, so we have this lunches out. We want to know if the mean of the lunches out variable is different from 3.5, so we press OK. All right, well, we see down here, if I can get my pen, there is the mean that was specified in the slide. So we had a mean of 3.94. And the question is that mean of 3.94 significantly different than 3.5? All right, how likely is it that we would find a mean of 3.94 in a population where the population mean was actually 3.5? All right, and our p-value is telling us that there is a 14.5% chance that this result is due just to chance or sampling error. All right, that means that if we reject the null hypothesis, there is a 14.5% chance that we are wrong, and we are only willing to tolerate a 5% chance of being wrong. All right, so if p is less than 0.05, we are going to reject the null. This is really making me miss the document camera. And if p is greater than 0.05, we are going to fail to reject the null. All right, so in this case, our p-value is greater than 0.05, so we are going to fail to reject the null hypothesis, which means, if we go back a slide, we are going to conclude that students are not eating more than half of their lunches away from home. All right, so we're concluding that students are eating roughly half of their lunches away from home. All right, the sample does not provide strong enough evidence to reject this null hypothesis, and so we are concluding that at the population level, we believe the mean is equal to this number that we have specified. All right, what always happens, all right, when we start to talk about this is people say, where does that 3.5 come from? All right, and that's a perfectly valid question. All right, where did I get 3.5 from? In this case, I got 3.5 simply from wanting to know, are students eating more than half of their lunches away from home? Another place, I wish I had the document camera for this, another place where the one-way t-test gets used all the time, and let me just get a blank sheet of paper to write on up here. Let's imagine that we ask people, actually, let me type in here while we're doing this. Sorry. Let's imagine that we ask people how much they like or dislike something, all right, on a 1 to 9 scale. And 1 means that they really hate this thing that we're asking about. And 9 means that they really love this thing that we are asking about. And if they answer 5, that means that they're perfectly neutral, all right? They don't love or hate it. And so one thing that we might want to know, if we ask a bunch of people to answer this question, then we might want to know, do people overall like this thing that we're asking about? All right, so let's say that this is a question asking, actually let me type because that's easier. Do you love or hate the marketing research course? All right, and so if I ask all of you guys this question, I know all of you would circle 9, but I might be curious to go back and find out, overall, do people like my course? All right, do people like this marketing research course? Now, if we look at these numbers, what would be the minimum number that someone could circle that would still mean that they liked the course? All right, so looking at this scale here, if they answer 5, they're indicating they're neutral, so they don't love or hate the course, which means that their answer would have to be greater than 5 to indicate liking for the course. All right, so if I look at the data from my sample and I find that the mean is greater than 5, that means that people like my class. Yay, all right? But if I look at the data and I find that the mean is less than 5, this means that people are saying they don't like the course. Boo. All right, so 5 becomes this cutoff point where at 5, people are saying they're perfectly neutral. If the mean in my sample is greater than 5, that suggests that maybe at the population level, people like the class overall. The mean is in the positive portion of the scale. And if the mean in my sample is less than 5, that provides some evidence that at the population level, people do not like the class, that they're answering in the negative portion of this scale. So one thing that we can do with a one-way t-test is we can ask, are people neutral? All right, is the mean equal to the midpoint of the scale, which in this case is 5, or are people not neutral? All right, they either love or hate this class. All right, and so in this case, 5 is our test value. And we have gotten this test value because in our question, do people, on a data analysis plan question, this might, sorry, I got to get the cursor all the way down there. If this were on the data analysis plan, I might ask something like, overall, do students love or hate marketing research? This question is asking, are students neutral, meaning their mean is at the midpoint of the scale, or do they love or hate it, meaning they're in the positive half or the negative half of the scale, and their mean to this question is not 5. All right, and so this is a place, this is what the slides are talking about over here. If you have a satisfaction scale ranging from 1 to 7, and you want to know if people are satisfied, all right, marking higher than the midpoint, then your test value would be 4. In this case, we could say this is dissatisfied and satisfied. If we want to know overall are people satisfied, we're asking, is their mean 5, or are they giving a number that's not 5? And specifically, we're interested in the case, the potential case that their mean is above 5. All right, but this is a common way that the one-way t-test is used, is we're not dividing the sample up into any groups. We're just saying overall, everybody, did people answer this scale in the high portion, all right, above the midpoint, or in the low portion, or were they right at the midpoint? All right, and this one-way t-test can accommodate that. I don't think I have an example of this in these slides because the specific data set doesn't really accommodate for that. If you're trying to work along in SPSS, we're using that student class example data set again. But when you go to the SPSS instructional video and we're working through that worksheet has an example of this in it. So you'll be able to see this in action in that worksheet. All right, let's look at another example of this. I'm gonna have to erase all of this or it's gonna show up on top of my SPSS. So in this question over here, I asked on the survey, how much money do you spend in a typical month on groceries? And I might want to know, do college students spend more than $100 per month on groceries? This 100 is pulled, completely out of thin air, but it could be that I read another study that suggested that 18 to 23-year-olds in America spend roughly $100 a month on groceries. So I want to know if my students at Ole Miss are like those other students, those other people aged 18 to 23 roughly. And so I could ask, are they also spending, $100 per month on groceries? Importantly, this question does not ask me to divide my sample up into groups. So there is no predictor variable. I am not dividing my sample up into groups to compare types of students. I have no predictor and I have a continuous outcome. All right, how much money they spend per month on groceries. It was measured on a ratio response scale. And so because I have no predictor and a continuous outcome, I'm going to do a one-way t-test. And in this one-way t-test, our null hypothesis is that the amount of money spent on groceries is equal to 100. So there's no difference between the dollars spent in the population and this reference point. And the alternative is that there is a difference, all right, that my population spends a different amount than this reference point. Before we actually do the test in SPSS, I'll just tell you that the mean is going to be $151 roughly, all right? And so this provides some evidence to suggest that maybe Ole Miss students are spending more than $100 a month on groceries, but we don't know yet if this is probably due just to error or if it's strong enough evidence to suggest there really is at the population level an average dollar amount spent that is higher than $100. To find out, we go back to analyze, compare means, one sample t-test. We are no longer interested in lunches out. Now we are interested in this groceries spent category. Our test value now is the number that we want to compare our mean to. So our test value is 100 and we click OK. All right, so the mean is off here a little bit. It looks like perhaps, I think I remember now in this set of slides, these slides are based on a sample size that is too smaller than this. So 2 people took the survey after I wrote these slides. I should go back and fix that. All right, but so we have $150.08 is our mean. And the question is that significantly greater than 100? To find out, we look at our p-value. Our p-value, remember, is where it says SIG. All right, so here's our t-statistic. Here's our p-value. With a p-value of 0.008, are we going to reject or fail to reject the null hypothesis? All right, remember our standard is if p is less than 0.05, we reject. All right, so in this case, p is less than 0.05, so we are going to reject the null, and we would conclude that students do spend a different amount than $100, but specifically the different amount is that it's larger than $100. All right, so we would conclude that students are, Ole Miss students are spending on average more than $100 per month on groceries. All right, so remember the goal of these tests is that we want to know something about students' behaviors. We could not conduct a census, so we drew a sample, and we want to know based on our sample, what do we think is true of the population? In this case, based on the answer that our sample has provided for us, we think that what's true of the population is that they are spending more than $100 on groceries. Importantly, when you draw these conclusions from statistical tests, you have to make sure that you are not concluding more than what the test says. This test does not tell us that Ole Miss students spend on average $150. Our sample spent on average $150, but this sample mean does not include an estimate of how much error there is in our measurement. All right, so in order to include that, we would have to construct a confidence interval and say, you know, I think that the true mean spending among college students is between X dollars and X dollars. We are asking a different kind of question. Instead of trying to come up with the specific number of dollars that students spend, which is what's called finding a point estimate, we are interested in this hypothesis test. We don't really care what the exact dollar amount is. We just want to know if it's greater than 100. All right, and this test has told us that, yes, we think at the population level, whatever the true dollar amount being spent by students is, we think that it's a number larger than 100. Okay. The next one, we're going to go to the independent samples t-test. So we will see more examples of the one-way t-test in that worksheet. All right, so in another video. All right, in an independent samples t-test, ignore all my notes down there. What the independent samples t-test does is it divides your sample into two groups, all right, on the basis of some categorical predictor. For example, men versus women, Greek versus non-Greek, freshman versus senior, white students versus black students. What are some others that we might have measured? Honor student versus non-honor student, student athlete versus non-student athlete. All right, importantly here with this two-way t-test or an independent samples t-test, you can only have two categories. All right, so the question will always talk about one category versus a second category. All right, and so here we have a variable that asks us to divide our students into two groups, male versus female, that's gender, a categorical variable. So we know we have to do one of these two tests. And the next thing that we have to ask ourselves is, what is it about these male and female students that we're interested in? And in this case, what we're interested in is how much money they spend on clothing. All right, so that spending on clothing variable was measured on a ratio response scale, which means it's a continuous outcome. And so if we have a categorical predictor and a continuous outcome, we are going to do an independent samples t-test. All right, so that's what we're learning about over here, an independent samples t-test. All right, so we might have a question on the data analysis plan that says something like, do female students spend more than male students on clothing? When we set up this independent samples t-test, our null hypothesis is always that the mean of group 1 is equal to the mean of group 2. All right, so in this case, I've written it as the mean dollar amount spent by women is equal to the mean dollar amount spent by men. And the alternative is always that the two groups are different. All right, so men and women do not spend the same amount of money. Right here we can see the issues. So this is a sample of 34 and our SPSS has a sample of 36, so we want to know, do men and women spend the same amount of money on clothing? Is the mean spending for the men equal to the mean spending for the women? We can look at our descriptive statistics for some suggestion as to whether or not there might be a difference. All right, so here we have the women. There are 18 women in the sample. Their mean was 235. Their standard deviation was this number. For the men, their mean was 16. I'm sorry, their sample size was 16 men, and those 16 men spent on average $112 a month on clothing. All right, so when we look just at this sample data, there is evidence that suggests that there's a difference between men and women in terms of spending. And the question is that difference strong enough to make us believe that at the population level, there is also a difference? All right, do we think this is a fluke of our sample, or do we think it's reflecting something true about the population? To find out, we have to do an independent samples t-test. To get that independent samples t-test, we're going to go to Analyze, Compare Means, Independent samples t-test. Here in the test variable box, we put the outcome variable that we're interested in, which here is how much money they spend on clothing. The test variable is the variable whose mean is going to be calculated. All right, so we can't calculate a mean of gender, but we can calculate a mean of clothing spent. So we're going to put that variable into the test variable box. And then down here in the box it's labeled grouping variable, this is where we tell SPSS, use this variable to divide my sample up into groups. All right, so we're going to put gender into the grouping variable box, and then we have to tell SPSS how those groups were coded. All right, and so in this case, somewhere I have an Excel sheet to tell me this that you guys can't see. In this case, Male is coded 1 and female is coded 2, right? So we're going to tell SPSS, because SPSS won't see male and female in the data set, they'll just see 1s and 2s. So we're telling SPSS, compare the people coded 1 to the people coded 2, all right, the men and the women, and press continue. All right, so we can see now it's going to divide the sample into 2 groups based on their answer to this gender variable. It's going to calculate the mean for each of these groups and then compare to see if those 2 groups have different means. All right, we're going to press OK. All right, and I should update these numbers here. All right, so there were 17 men with an average spending of $117.65, and there were 19 women with mean spending of $223.23 and a standard deviation of 364.69. All right, so sorry about that part. We come down here, we're looking for our test statistic and our p-value. Let me get my pen back. Here is our t statistic and here is our p-value. All right, when we are doing this test, unfortunately, ignore those. When we do this test, some things get printed out that we don't care about. All right, let me make this wider for just a second. All right, first question that people always have, which line am I supposed to be looking on? Look on this top line. All right, pretend like this second line doesn't exist. This makes an assumption. We're not going to get into the assumption, but let's just look at it. We're just making this assumption that there are equal variances, and we're just going to stick with this top line. This box right here is doing a separate test that is not the t-test. All right, this is doing a test for equality of variances, which is asking, are these 2 numbers the same? All right, this right here is our t-test, comparing if the means are the same. And this f-test right here for equality of variances is asking if the variances are the same between the men and the women. We do not care about this test. Those are not the numbers that we're looking for. We are looking for this t statistic and the p-value that comes after it. All right, so for this test, our t statistic is negative 1.119. The reason why t is negative is because when SPSS does this test, they say the mean for men minus the mean for women produces a negative number, and then they test to see if that number is different from 0. All right, so if men and women are the same, then the difference would be 0. If men and women are different, then they would have a non-zero difference. Because the men's mean is smaller than the women's mean, we get a negative number here, and as a result, our t statistic is negative. If we had entered the code for women first and the code for men second, these numbers would be swapped. We would get a positive number here. Our t statistic would be the same exact number. It would just have a positive sign on it. All right, so this negative number does not mean that you did something wrong. It's just telling you about the order of the means in this box. All right, so we have this t statistic of negative 1.12, a p-value of 0.27. With a p-value of 0.27, are we going to reject or fail to reject the null hypothesis? All right, remember we're rejecting the null hypothesis if p is less than 0.05. In this case, p is greater than 0.05, so we are going to fail to reject the null. All right, let me erase all this so we can look back at the PowerPoints. All right, remember we're failing to reject the null here because our p-value is greater than 0.05. That p-value means there's a 27% chance that we found this result due just to chance and sampling error. And if we rejected the null hypothesis and concluded there was a difference at the population level, there's a 27% chance that we would be wrong when we did that, right? And that's too big of a chance to be wrong, right? So in this case, we would fail to reject the null and we would conclude that men and women spend the same amount of money on clothing. Now, I love this example because this is a very difficult pill to swallow, all right? We are looking at these means over here. The women's mean is almost twice as large as the men's mean, and yet somehow the SPSS comes back and says men and women spend the same amount. All right, and then a bunch of people want to throw up their hands and say statistics are garbage. This is why I don't look at this stuff. All right, obviously the numbers show that there's a difference. How can we possibly get this result? Let me tell you. over here, in addition to the mean, we have these descriptive statistics, the standard deviation. The standard deviation for the women is 364. The standard deviation for the men is 142. If you'll recall, when we talked about descriptive statistics, we learned that what the standard deviation shows us is how spread out people's responses are. So what this means is that the men's answers are relatively close together, all right, around their mean of 117. The women's answers, though, are really spread out around their mean of 223. All right, so that means there are some women who are spending very little money and some women who are spending a lot of money. And in fact, it's not even some women that are the problem here. It is an outlier. All right, so if we go and look at the actual data and we go to this clothing spent variable, if you scroll down, you will see this one woman right here who indicated that she spends $1,500 per month on clothing, right? Her $1,500 per month spending is way higher than the average, and it's way higher than most of these other values that we see here in the column. Because of that, her presence in this data set and the fact that the standard deviation becomes so large because of her very high answer that's very far away from the mean, the statistics look at this and say, maybe there is a good chance that the women's mean is higher only because this one person was drawn out of the population and put into the sample. If by chance we had drawn a sample that she was not included in, we would no longer see this high of a mean for the women, all right? We would see a much smaller mean because her outlier response would not be dragging the mean towards it. So as a result, SPSS is rightly acknowledging that the women's mean is only so high because of this one woman. And so maybe at the population level, men and women aren't different. It's just this one woman driving the difference in our relatively small sample. And in fact, if we get rid of her from the data set and we do the test again, what we see now is that the means are 117 for the men and 150 for the women. And while there's still, some difference between the men and the women, the difference is nowhere near as extreme as it was in the presence of that woman. And so now it's much easier to accept, okay, maybe this evidence isn't strong enough, right, to suggest a population level difference between men and women. All right, so we can see how the presence of just one anomalous answer in the data set can affect the results, and how the analysis is rightly acknowledging that if that one anomalous result was not in the data set, we might have seen something completely different, and that that dampens our ability to make predictions about the population. So it makes us want to be more conservative and say, I don't know, this is probably just a function of this woman's presence in the data set. Her presence in the data set also helps us, let me use a different option, helps us see why it's important to use the median versus the mean when you have outliers in your data set. So if we ask for the mean and the median here, we can see that the mean spending, this is for everyone, right? So it's including everyone in the data set, not just the women, but the mean spending is $173 and the median spending is only $80. So that one outlier in the data set is really dragging the mean towards that outlier. And if you wanted to say, on average, here's how much Ole Miss students spend on clothing, whether you report the mean or the median based on this sample would have much different implications, all right, for what people think is a typical amount of spending for students. All right, so a little deviation there because of a serendipitous outlier in the data set. All right, let's return to our examples. Here's another example. Do Greek students eat dinner away from home more often than non-Greek students? All right, so returning to our table, trying to figure out how to use this table. Does this question ask me to divide my sample into groups? Yes, it does. All right, it's asking me to divide my sample into Greek and non-Greek, which is a categorical predictor. And then what is it that those Greek and non-Greek students are doing that we're interested in? All right, they're counting how many dinners away from home they eat, which is a continuous variable. It's a ratio response variable. So we have a categorical predictor and a continuous response. So we're going to do an independent samples t-test. And that independent samples t-test is going to ask, is the mean number of nights out for Greek students equal to the mean number of nights out for non-Greek students, or are they different? All right, and so we can see down here some descriptive statistics that I'm going to have to update to include the 2 other people who took the survey. But it looks in our data set like the Greek students are dining out more often than the non-Greek students. And we can see if this difference is statistically significant by doing an independent samples t-test. All right, so we're going to go to Analyze. Where am I? Compare means, independent samples t-test. All right, we're no longer interested in clothing. We are now interested in dinners out. And we're not interested in people's gender. Now we are interested in whether or not they are Greek, which is still coded 1 and 2. So we can leave that 1 and 2 in the boxes. Press continue and click OK. All right, so pardon me while I update these means over here. Greek should be 16 with a mean of 4.5. and the standard deviation of 1.16. Non-Greek is 20 with a mean of 3.2 and a standard deviation of 2.12. Okay, so we have, let me get my pen back. We have the sample means right here. And we want to know if those sample means are statistically different. So we look for our t statistic and our p-value. All right, our p-value is 0.034. All right, because p is less than 0.05, we are going to reject the null hypothesis. All right, so we're going to conclude that Greek and non-Greek students are not the same. All right, we're siding with this alternative hypothesis. We think, based on the data that our sample has provided, that at the population level, Greek and non-Greek students are not dining out at the same rate. And specifically, our means suggest that Greek students are dining out more often than non-Greek students. All right, so we've taken data from our sample and used it to draw a conclusion about what we think is true with respect to this question at the population level. All right, and so that's why we do these inferential tests, because we have to account for the influence of error in our measurement. And we're asking, yes, I see a difference in my sample. Do I think that difference is just due to error? All right, that's what my null hypothesis is saying. Any difference is likely just chance or error. Or my alternative is that it's not error. It's reflecting a real population level trend. All right, that Greek students really are dining out more often than non-Greek students. All right, the last kind of t-test is called a paired samples t-test. All right, and the paired samples t-test, going back to this table, we have this question: do students spend more at restaurants and bars than they do on groceries? All right, and so we have to ask ourselves, when we see this question, if this were a question on the data analysis plan, does this question ask me to divide my sample up into groups? All right, so I don't see anything here that suggests that my students, or that my sample needs to get put into 2 groups. I just see this phrase, do students. All right, so this is all the students. So I have no predictor. All right, so I'm going to be doing one of these 3 tests. It's either going to be, the answer now either has to be chi-square goodness of fit, one-way t-test, or paired samples t-test. So the next thing that I have to look at is, what are these students doing that I'm interested in? And in this case, they are spending money in restaurants, which was measured on 1 question in the survey, and they are spending money in bars, which was measured on a 2nd question on the survey. All right, so I'm looking at the data that all of my students provided to 2 continuous measures. How much do you spend in restaurants, and how much do you spend in bars? All right, and I want to know if their mean response on those 2 separate questions was the same or different. All right, so I have no predictor, 2 continuous outcomes. I'm going to do a paired samples t-test. Now, in case it helps you, all right, I don't know, to be honest, I don't know what helps, because I have never asked about it in a survey question. This is called an independent samples t-test because it's comparing the means of 2 independent samples. For example, the mean of men versus the mean of women. These samples are independent because there is no overlap here. All respondents are either placed in this group or this group, and no respondent can exist in both groups. All right, so we have the answers of one independent group being compared to the answers of another independent group. In a paired samples t-test, we are comparing everyone's answer on question 1 to their answer to question 2. Everyone who answered this question also answered this question. So each person who answered the survey is providing a pair of data points. All right, their response to question 1 and their response to question 2. These two samples are not independent of each other. It is the exact same people answering question 1 and answering question 2. And we just want to know, are their answers to these two questions the same or different? All right, so that's what the independent and the paired in independent and paired samples t-test means. All right, so here we want to know, are students spending more at restaurants and bars than they're spending on groceries? All right, so we had these two spending categories on the survey. It asked, how much do you spend per month in restaurants and bars? How much do you spend per month on groceries? And we want to know, is the mean on dining equal to the amount spent on groceries? All right, remember the null hypothesis is always a hypothesis that there's no difference. So there's no difference in spending in these two categories. And the alternative is if there is a difference, all right, that students are spending more in one category than they are spending in the other. To do a paired samples t-test, I think this might be the easiest one. We go to Analyze, Compare Means, Paired Samples t-test. And all you do here is enter the pair of variables that you're interested in. So we're interested in dining spent versus grocery spent. All right, SPSS opens up this second line in the event that you wanted to enter a second pair of variables, but you don't have to enter anything here. All right, we're not going to. You just leave that line completely blank, and then you press OK. That's it. All right, so I'm not going to update these means because I don't want to waste your time having to watch me do that. But we can see that the mean for dining out is roughly $265. The mean for groceries is roughly $150. That provides some evidence to suggest that students are spending more on dining out than they're spending on groceries. The question is that difference significant? All right, and so to find out, we come down here, we look in our table for where it says T and SIG. Here is our T statistic, here is our p-value. All right, so in this question about whether students are spending more in one category than the other, we have a p-value of 0.004, all right, which is less than 0.05. So we are going to reject the null, and we are going to side in favor of the alternative hypothesis. Now our next step is that we have to write our result in plain English, all right? And so here we could conclude at its most abstract that students do not spend the same amount in restaurants and bars that they spend on groceries, or we can look specifically at these means and say, students do not spend the same amount in these two categories. Specifically, students are spending more on dining out than they're spending on groceries. All right, so this is what we've learned from this test. We have this data from our sample. Based on that sample data, we wanted to make an inference at the population level about all student spending. And from this data, we feel confident to conclude that students are spending more on dining out than they are spending on groceries. All right, because when we reject this, there is only a 0.4% chance that we're wrong when we do that. All right, so we have very strong evidence to support a conclusion that students are spending more in one category than in the other. All right, so this paired samples t-test is looking at the difference between answers to two questions on the survey without dividing the sample into groups. Just everyone who took the survey, was their answer on question 1 the same as their answer on question 2? All right, so this is my only paired samples example here. I have something that I normally write up on the board. The next time I can get to that document camera, I will record just a short video to separate the paired samples t-test from correlation, which we're about to learn about. So look for that on YouTube. Let's look at correlation though. All right, so correlation is something that I think everyone thinks that they know exactly what it means. But the problem is that correlation is a word that gets used colloquially all the time. But the way that we use it in everyday language is wrong. All right, and so the thing about correlation, the thing that people say wrong, is that they always try to say things like there's a correlation between gender and let's say income, or there's a correlation between I don't know, year in school and something else. The problem with that is that correlation is a description of a relationship between variables, but it's a specific relationship between two continuous variables. All right, so in order to do an analysis of correlation, you have to have two continuous variables, a continuous predictor and a continuous outcome. All right, and so what this correlation is measuring is as the first variable increases, so as variable 1 increases, what tends to happen to variable 2? All right, does variable 2 also tend to increase? Does variable 2 tend to decrease? Or is there no relationship? So variable 1 goes up and sometimes variable 2 goes up, but sometimes variable 2 goes down and the two don't appear to be related at all to each other. All right, so this correlation coefficient is telling us about the covariation between two continuous variables. So if you see a change in one variable, can you predict what will happen to the second variable? All right, that's what correlation is measuring. You cannot have a correlation between gender and income because gender is a categorical variable. All right, and so you cannot assess the amount of change, all right, between nominal variables, so you cannot report correlation. There are other kinds of analyses that you could do to look at that sort of thing, but correlation is not it. All right, so this says first step in determining correlation. When you're actually doing the analysis in SPSS, you don't look at a scatter plot first, but one thing that people like to look at often is a scatter plot of the data to help them figure out if there's a correlation between their two variables. And so what we're looking at in the scatter plot, what we're looking for is, do the points, and I'll show you the points in just a second, each point represents a person's pair of answers to two questions. Do those points seem to form a line, or do they just form a big cloud? All right, suggesting that there's no relationship. All right, and so we are going to look at two possible hypotheses here from, two possible relationships here from our survey. Is there a relationship between the number of meals that students consume away from home and the dollar amount that they spend on first dining out and second groceries? All right, so we're asking, as students, we will say dine out more, how does that affect money spent on dining? All right, we would expect that to go up. Presumably, as you go out for more meals, you spend more money in restaurants. And the second thing is, as students dine out more, what happens to how much they spend on groceries? All right, and I might hypothesize a negative relationship here, that if you are dining out for all of your meals, then you would not need to spend much money in the grocery store. So presumably, as you go out for more meals, your amount spent on groceries should decrease. All right, so we can look at the scatter plots of this actual data from the survey here. Here is the scatter plot for dining out versus meals out. All right, so on the x-axis down here, this is how many total meals students reported eating away from home. This is breakfast plus lunch plus dinner in the week. So the range was between 0 and 21. All right, there was one person here who said they eat 21 meals away from home. And then the second question is, how much do you spend in restaurants and bars? So that's what's on the y-axis. And so each dot represents a single respondent's pair of answers. All right, so for example, this person, the first number 8 in those parentheses is saying this person says they eat 8 meals away from home and they spend $400 a week on those 8 meals. All right, so those are some expensive meals that person's having. This person over here appears to be more value conscious. They are eating 21 meals away from home and spending $336 on those 21 meals. In this scatter plot, if we're trying to see if there's a relationship here, we're looking to see, do these dots form or seem to form a line? And in this case, this black line that's drawn over the dots is what's called the line of best fit. If this line of best fit has a positive slope, meaning that it moves up as we move from left to right, this means or suggests that there's a positive relationship in the data. So as people's answers to this question, how many meals do you eat away from home, increases, their answer to this question, how much do you spend, also tends to increase. If this line were, where's my pen? If this line were flat, that would suggest that there was no relationship, all right, that there was just a cloud of dots with some people spending a lot and some people spending a little, but there was no clear pattern. And if this line had a negative slope, all right, so it moved down as we move from left to right, that would mean that there was a negative relationship. So as this variable increases, this variable decreases, all right? And this is how we talk about correlations. As this thing increases, what tends to happen to this thing? All right, so we see the scatter plot for dining out here. Let's look at the scatter plot for grocery spending. Here we have this somewhat flat line, or it has a barely positive slope, but it looks pretty flat. And this is because we can see in this cloud of dots that we have this range of students eating meals out again. All right, here's our person eating 21 meals out. And we ask how much they spend on groceries. Some people who eat few meals out spend very little on groceries. Some spend a lot. Some people who eat a lot of meals out spend very little. Some spend a lot. All right, so it doesn't look like there's a clear pattern here, all right, between how much people spend on groceries and how frequently they dine out for their meals. Now, we can test statistically to see if these patterns are significant, all right? And the way that we do this in SPSS is we go to Analyze, Correlate, Bivariate, all right? And we enter the two variables that we want to look at a correlation between. So first we can look at total meals out and groceries spent. We just move those two variables over. Those are the two variables that we want to know if they're correlated with each other. We click OK. All right, now this gets printed out and everyone hates it because they look at this table and they say, what on earth is happening here? This table has 4 cells. All right, you see these 4 cells here. What's happening in this table is that they are giving you all possible combinations of these two variables. All right, so we have 2 variables times 2 is 4 possible combinations. So the correlation between total meals out and itself is 1. All right, the 2 variables are perfectly correlated with each other. There's no p-value. And we see that same thing here for groceries spent correlated with groceries spent. All right, it's 1. On this diagonal, all the variables will always be 1. What you're interested in looking at is one of these 2 cells, and they have the exact same numbers in it, so it doesn't matter which one you look at. This is giving you the combination of total meals out and groceries spent. This is giving you the combination of groceries spent and total meals out. In correlation, it does not matter which variable goes first, all right, in the pair, because we're just asking, are the 2 related to each other? We are not asking if one causes the other one to happen. All right, so this right here is our correlation coefficient R. R is a number that varies between -1 and 1. When R is 0, that means that there is absolutely no relationship between these 2 variables, that knowing someone's answer to this question would give you absolutely no ability to predict their answer to this question. At the extremes of -1 or 1, that means these 2 things are perfectly correlated. If the correlation was 1 or -1, that would mean that if you knew how many meals someone dined out, you could perfectly predict how much money that individual person spends on their groceries, because there is a perfect one-to-one relationship, all right, between these 2 variables. Negative means that there was a negative slope. So as one variable increases, the other one decreases. +1 means there's a positive slope. So as one variable increases, the other one also tends to increase. I have never in my life done an analysis and gotten a result of -1 or 1. So most often you are going to get some number that is between 0 and one of the extremes. In our case, we have a correlation of 0.092, and right beneath it is our p-value, all right, 0.593. I'm gonna write that over here. 0.593 is our p-value, all right? And we can do this analysis again. Let me erase all of this stuff. All right, I can do this analysis again, looking, analyze, correlate, bivariate, not at groceries spent, but now at dining spent. All right, and now we see that our correlation coefficient is 0.644, and our p-value is 0.000. And the reason why this has asterisks next to it is because SPSS will flag or put little stars next to correlation coefficients that are significant, all right, where their associated p-value is less than 0.05. P can never actually be 0. What's happening here is that the p-value is so small that when SPSS rounds to 3 digits, those first 3 digits are all 0. All right, so it just reports 0.000. So this is just a very small number as our p-value. All right, so correlations, just like every other kind of analysis, have a null and an alternative hypothesis. We did not talk about that yet. Let me erase these marks over here. For a correlation, the null hypothesis is always that there is no correlation, all right? Which means that R would be equal to 0. Remember, the null hypothesis means maybe you see a small correlation in your sample, all right, like 0.092, but I think that that correlation in the sample is due just to chance or sampling error. I don't think it reflects a real population level relationship. All right, so if we fail to reject the null, we're concluding there's no relationship, no correlation between these two variables, which is what would happen here because P is so much larger than 0.05. And when we reject the null, all right, because P is less than 0.05 and we side with the alternative is that yes, there is a correlation, all right? So R is significantly different from 0. There is a relationship between these two variables. All right, so if we were gonna write up this result in plain English, we might say there is a relationship between number of meals away from home and money spent in restaurants. Let me make this bigger so I have more room to type. All right, as students consume more meals away from home, they tend to spend more in restaurants. However, there is no relationship between number of meals consumed away from home and dollars spent on groceries. All right, so those two things, let me move this because I'm not sure what you guys can see. Those two things seem to be unrelated to each other. All right, so how much you spend or how often you go out for your meals does not seem to be related based on our data to how much money is spent on groceries, but as makes sense, as students spend more time in restaurants, they tend to spend more money in those restaurants. All right, so this is what the correlation is telling us. The null hypothesis is always no correlation. The alternative hypothesis is always yes, there is a correlation. All right, in the next few screens, I'm going to give you like some additional things to think about with correlation. So let me erase all of this stuff so that we can get to them. And then I want to show you an example, you know, being a consumer of other people's data kind of thing. Okay. One thing before we get to the considerations. Sometimes when people talk about correlations in papers, they have a question about, well, how should I describe the strength of the relationship? All right, so this table is assuming that SPSS has told you that your correlation is statistically significant, all right? Because if you do the test of correlation and your p-value comes back greater than 0.05, you always report there is no correlation, regardless of what that correlation coefficient was. But if SPSS says you do have a significant correlation here, this is language that is often used to describe the strength of that relationship, all right? Remember, what these numbers are reflecting is your ability to predict someone's answer to the second question based on their answer to the first question. When the number is lower, you have lower predictive power, meaning there's not that much of a relationship there, so it's hard to make a prediction about that second variable. And when the number is higher, that means these two things are really tightly related. So if I know your answer to question 1, it would be very easy for me to predict your answer to question 2. All right, and so that's what this strength of association is talking about. One consideration, all right, I think this says, oh, there's gonna be more considerations in a couple of slides. First big consideration, I've said it already in class, I'm gonna say it again here. Correlation does not equal causation. What correlation is testing is, are two variables related? All right, it is specifically testing a question about, if you know the answer to one question, could you predict the answer to the second question? And importantly, that prediction, let me erase that, I don't know what I was writing there. That prediction can go either way, all right? So if you have two variables, A and B, and you wanna know if they're related to each other, if a correlation, if it comes back and you find out that these two things are correlated, that means that you could use this variable to predict that one, or you could use A's answer to predict their answer on B. All right, it doesn't matter. A relationship just means one variable can be predicted with information about the other variable. Causal data, all right, causation, you have to have an experiment to demonstrate, right? Because of all those things that we talked about eliminating other causal factors, making sure there are no confounds in the experiment, all right, so that if you find a relationship between two variables, nothing else can explain it besides the thing that you manipulated. Correlation doesn't do that. All right, so the survey is not controlling for anything. You just have two pieces of information and you want to know if there's a relationship between them. This is problematic as, you know, thinking of us as consumers of other people's research, because when we talk about the word correlation in everyday language, I think that people think that it means causation. All right, and so we often see news headlines where people take correlational data and then use language that suggests a causal relationship, even though causality has not been tested, all right, with that study design, all right, or in that data. Some examples. This first one, looking to shed a few pounds before the holidays, new research shows that reading food nutrition labels may help you shed those pounds. All right, so in a survey of 25,000 Americans, those who reported scrutinizing labels while grocery shopping had lower BMIs and weights than those who paid less attention to what was in their food, and the difference was especially pronounced for women. All right, so to me anyway, the wording of this headline, reading food nutrition labels may help shed a few pounds, suggests that the act of reading nutrition labels can help you lose weight. All right, that reading nutrition labels leads to weight loss. All right, is it that easy? All right, would anyone in the United States or in the entire world be overweight if all they had to do to lose weight was read a nutrition label? All right, the answer is no. All right, merely reading the label on a box of food or a bag of food is not going to cause you to lose weight. What's probably happening here is that, yes, reading nutrition labels probably is correlated with weight, because people who read nutrition labels probably also do other things that leads them to have low weights, like not eat food that has poor nutritional content based on what that nutrition label said. They may also be more likely to exercise, all right, or drink more water, or sleep more, or do all of the other things that we know lead to healthy BMIs. All right, so this title seems to suggest a causal relationship when in reality it's just talking about a correlational relationship. All right, in medical research, it's almost always correlational because oftentimes it is unethical to assign people to treatment groups when you are unsure of how the outcome might adversely affect them. What do I mean by that? That was like a sentence that didn't make much sense. This headline, C-section births increase the risk of autism by 23%, study finds. Pregnant women are a protected research group, meaning that most of the time you can't do any research on pregnant women. But even if you could do research on pregnant women, no one would ever agree to participate in a study where they would be randomly assigned to a vaginal versus a C-section birth, right? Nobody would agree to that at the outset, that no matter what, I agree to give birth in one of these two ways, regardless of any other medical, stuff that happens to arise, right? And so for that reason, these kinds of studies rely on what are called cohort studies, where they take groups of women that have C-sections and compare them to groups of women that do not have C-sections, and then they look for differences between those two groups. That's correlational, all right? They are measuring whether or not they had a C-section. They're not manipulating whether or not they had a C-section. They're just measuring, did you have a C-section, yes or no? And then they're looking to see if that's related to other possible outcomes, like in this case, risk of autism. The problem here is that this headline suggests that having a C-section is going to cause your baby to have autism. That doesn't make any sense. All right. What's probably happening here, and I'm not going to pretend that I'm an obstetrician and that I know how all of this stuff works, but what's probably happening here is that some genetic factor that contributes to children having autism may also be contributing to women needing C-sections. All right, so it's one of these spurious correlation things where you have two things that look related to each other, but there's in fact some third variable that's leading to both of them happening. All right, and so in this case, I'm guessing that that's probably what's happening. There is some other thing that's going on that's both leading women to need sections, C-sections, and is also leading their children to be more likely to have autism. All right, finally, lighter example, like one of my favorite examples from the news. This is now 5 years old, unfortunately. Great examples don't come around every day, so we have to hold on to them for a while when they do come around. This was, it got a lot of popular press coverage in 2014 when this study was released, but this one was from the Today Show. Few things set engaged couples into the boxing ring faster than how much to spend on their wedding, but a new study from Emory University economics professors indicates that moderation in all things leads to, that's causal language, a longer union. All right, and so what they argued in this Today Show article, or it was a kind of light coverage of this economics article, was that not spending very much on the engagement ring leads to a longer marriage. That is causal language, all right, leads to. They should say is related to. This study is correlational. All right, and so I was really interested in what was actually found in this study because, I don't know, because it's interesting sounding, but also because it was a good class example. So I went to the actual economics paper that these Emory University's professors published, and I found that they did this correlational study. It's called a hazard study, or they're looking at risk rates. And so they took all of these factors that they got from people on their surveys, and then they looked at this outcome, getting divorced or not, and they looked to see which of these things were correlated with getting divorced and which of them were not correlated with getting divorced. All right, and so things increasing the hazard of a divorce. Bride is currently in college or a college dropout. The groom is employed part-time. They are living on the poverty line, basically. The husband and wife have some differences in age, race, or level of education. The bride believes the groom's wealth is important. The groom believes the bride's looks are important. The groom spent $2,000 to $4,000 on a ring, and the wedding cost $20,000 or more. All of these things increased the hazard of divorce. On the right-hand side, things that decreased the hazard of divorce. Husband has a college degree. Wife is employed part-time. As income increased, there was less likelihood of divorce, all right, with a combined income of $125,000 or more having the lowest association with divorce. The couple attends religious services. They have at least one child together, whether or not they were married when that child was born. They report knowing each other very well. They went on a honeymoon. A lot of people came to their wedding, and the wedding was inexpensive. All right, so the lowest risk of divorce was when the wedding was super inexpensive. All right, so looking at all of these factors, you can ask yourself, what's really going on here? All right, is this a story about the cost of an engagement ring? All right, or are all of these pieces of information telling a different story? All right, and the authors actually tell you what's going on here. Just the Today Show apparently didn't want to talk about it in the article. The authors suggest a mechanism here of debt stress. All right, so basically debt stress is this third variable that all of these things are related to. So these things are related to divorce, but they're related to divorce because they contribute to debt stress. All right, so if the bride is currently in college or a college dropout, the groom is employed part-time, the couple makes almost no money, the bride believes wealth is important, and they spent a lot of money on the ring and the wedding, they are probably having a lot more debt stress than people who have a lot of education, they have a high household income, they did not spend much on their wedding, right? And so it's the debt stress that's leading to divorce, right? It's not how much you spent on a ring. All right, and so the bottom line to this article, men and women in this class, should you decide to marry in the future, is that it does not appear that what you spent on the ring is what matters. It appears that whether you can afford what you spent on the ring is what matters. All right, so overall, the story is if you want to decrease your hazard of divorce, live within your means. All right, I feel like that's pretty good advice overall for everyone, whether you're looking at getting married or not. All right, last consideration about correlation. All right, so we have this first thing. Correlation does not necessarily equal causation. Be especially careful about this when you're looking at news headlines and ask yourself, if they use causal language, did they really do an experiment? All right, or are they talking about a correlation but using causal language to describe it? Additionally, when you are reporting a correlation, the correlation needs to be significant to imply a relationship at the population level. All right, so just as two means can be mathematically different, but not statistically different, two variables can appear related in the sample, all right, but we can still draw the conclusion that there is no relationship in the population. All right, so it still comes back to the p-value. Does the p-value indicate that we're going to reject the null and conclude there is a relationship, or is the p-value very large and we think this relationship exists as a fluke of our sample? All right, and finally, correlation requires two continuous variables. All right, so you need to have a continuous variable that is your predictor. In the ADHD survey, this will tend to be things like age, or maybe a question like, is how often students take this medication related to their GPA? So you have how often they take it is a continuous variable related to their GPA, which would also be a continuous outcome. The short video that I'm going to record soon is going to look at the difference between correlation and a paired samples t-test. But one thing that I just want to point out here, correlation is talking about a relationship. Is this variable, this continuous predictor, related to a continuous outcome? Relationship. A paired samples t-test is talking about a difference. Did people answer question 1 differently than they answered question 2? All right, so you can look at the language in the question itself to help you figure out if the question is referring to two continuous variables. Is it a relationship question, which suggests I need correlation, or is it a difference question, which suggests I need a paired samples t-test? All right, so this is all I have about t-test and correlation. Look for that short video to help separate correlation from a paired samples t-test coming to the YouTube channel soon. Please watch some of those other videos that I posted from other authors, I don't know, video makers. If you're having difficulty with the conceptual aspects of some of these statistics, all right, so they talk about it in slightly different ways. They have lots of visual graphics that I don't know how to make, so they have some visual things that might help make things make more sense. All right, so please refer to those as you are looking at these topics so that you get the best understanding that you possibly can. If you have questions, please leave them as comments to the YouTube video or send them to me in an email, all right, so that I can make sure that you and the rest of the class get those answers so that we can all stay on the same page. All right, wash your hands. I'll see you next time.